Okay, so we're still working with the simple harmonic oscillator in quantum mechanics, and we move now over to the energy basis, and we're working with these operators A and A dagger, which we said now are the dimensionless Hamiltonian is A dagger A plus 1/2. We showed that the commutator for A and A dagger is 1. If you reverse that, the commutator of A dagger and A is -1. The commutator of A and the dimensionless Hamiltonian just gives you A back again. And the commutator of A dagger with the Hamiltonian gives you minus A dagger. So it gives you the negative of that. Okay, so now let's start looking at the energy. So what if we apply an operator product of the Hamiltonian and the A operator with our dimensionless energy states? So that means that what I could rewrite this as is, so HA is the same thing as taking AH minus the commutator of A and H. Or, if I want to go back and show where that came from, if I take the commutator of A in the Hamiltonian, that's just A times the Hamiltonian minus the Hamiltonian times A. And so if I add this to both sides, and I get this, and if I subtract off the commutator, I get A times the Hamiltonian minus the commutator, like so. Okay, so now let's apply that to the energy. Sorry, let's apply that to the dimensionless energy eigenstate. Okay, so, well, the commutator we just worked out was A. So that's AH minus A times the energy state, which we can now break up, and we have AH operating on the eigenvector minus A operating on the eigenvector. Now, the Hamiltonian operating on the energy gives us the energy again. So that's A times the energy eigenvalue times the eigenvector minus A times the eigenvector. The energy eigenvalue right here is just a number, so I can bring it out in front of the operator. So I get E, or epsilon A acting on the eigenvector minus A acting on the eigenvector, which I could then factor out. So I have epsilon minus 1 times A times the eigenvector. So what this tells me then is the Hamiltonian operating on A, which operates on the eigenvector, gives me the energy minus 1 times A operating on the eigenvector. So this implies then that our operator A lowers the energy by a step of 1. So that means it brings down the energy from epsilon to epsilon minus 1. So we could just, but now we don't really know what happens when A operates on the energy state. So what I can do is I can say A operating on the energy state gives me an eigenvalue C epsilon minus 1. So I've dropped it from an energy state epsilon to the energy state epsilon minus 1. So it's a lowering operator. It lowers the energy state. And this eigenvalue is just a constant. So A now has lowered the energy state from one level to the next. So if I was to draw kind of a cartoon of quantized energy states, so this would be epsilon 1, epsilon 2, epsilon 3, epsilon 4, so forth, then A would take our particle in this state and move it to the next lower state. So that's what the operation of A on epsilon does. It moves it from one state down into the next energy level. Similarly, if we were to take the product of the Hamiltonian and a dagger operating on the energy state, then we would get, I could write this as a dagger H. Minus a dagger H commutator, all of that acting on the energy state, which gives me a dagger H operating on the energy state, minus a dagger operating on the energy state. So I get a dagger H operating on the energy gives me epsilon plus a dagger epsilon. And if I factor it out, I get epsilon plus 1 times a dagger operating on the energy state. So if a dagger operating on the energy state now gives me an eigenvalue C epsilon plus 1, and now changes the energy state from epsilon to epsilon plus 1, where again this eigenvalue is a constant right here. So now what a dagger does is a dagger raises to a higher energy state. So if I look at my energy levels again, a dagger operating on epsilon is going to take me from a lower state up to the next higher state. So it raises it in energy. So it's an operator which jumps from a lower energy state to a higher energy state. So that's why these are sometimes called the lowering operator and the raising operator. So now we can kind of see their actions. So these operators, A and A dagger, which are just combinations of position and momentum, in the energy basis, take an initial energy state and move it into a higher energy state. So what we could do is we could do this consecutively. So we could say take A and apply it to epsilon, which would then give us the eigenvalue C time and move it to the new state epsilon minus 1. We could apply A again to epsilon minus 1, which would give us C epsilon minus 1, and now move us to epsilon minus 2. So you notice in the subscript, I'm taking the old name and applying it to the subscript and then creating a new state right here. So we keep doing this dot, 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 all the way down to basically 0 energy, and you can't lower any further than 0. So A operating on the 0 state would give us a 0. You stop right there. With the raising operator, we can do the same thing. So that would get C epsilon plus 1, epsilon plus 1. So now you notice that the subscript here is the same as the new energy state. And I could apply A dagger to epsilon plus 1, which would give me C epsilon plus 2 times epsilon plus 2 energy state. And I could go, etc., up to infinity, really. I could keep going as long as there's energy allowed. So now, the interesting thing is I could take the product A dagger A and apply it to the lowest energy state here, and that would give me A dagger times 0, which would give me a 0. So applying A dagger A to the lowest energy state, 0, just gives me a 0. So now, if you remember, the dimensionless Hamiltonian was A dagger A plus 1/2. So that means that A dagger A is equal to the Hamiltonian operator minus 1/2. And so if you put that in, you get the Hamiltonian minus 1/2 operating on the lowest energy state, which is equal to 0. So that means that my Hamiltonian operating on the lowest energy state minus 1/2 times the lowest energy state equals 0. So the Hamiltonian, when it operates on the lowest energy state, gives me a value of 1/2. So I could rewrite this then as the lowest energy, epsilon 0, is 1/2, which means that lowest, that's the lowest energy divided by h bar omega is equal to 1/2. So the lowest energy that you can have is 1/2 h bar omega, which is exactly what we found when we used the Schrodinger approach. We found that the lowest energy you can get is 1/2 times h bar times the frequency of the oscillator. And so we've done this now without having to actually solve the Schrodinger equation, without solving a second order differential equation. We did it entirely with linear algebra and vector, linear vector states, and just a kind of a interesting combination of position and momentum operators to give us this thing called the lowering and raising operators. But with that, we're able to redefine the Hamiltonian, and from that, we're able to show that the lowest energy state was 1/2 times h bar times omega.